Okay, thank you. Thank you very much, Claire, for a most interesting talk. And thank you very much, Ricky, for putting me on after such an interesting talk. I've come to, as a chemist, really, I'm fraternising with the enemy, talking to fire safety engineers, and obviously my interest is more towards the chemistry side. But what I'm trying to do is to get something to get you to look in terms of what chemistry provide, in terms of the behaviour of materials when they're burning, and to see whether that can be implemented within your fire safety engineering codes. So, the first thing obviously to do when you speak to an audience that aren't particularly your own congregation is to insult them. So I thought I would preach to you, at least initially, about what fire safety engineering was in my simple chemist's way. The goal is to protect people and property from unwanted fires, and there's a picture here of a fire disaster actually in Poland. I would say it was a failure of fire protection engineering, even if it wasn't a failure of fire safety engineering. The materials that the hostel was made out of clearly weren't able to withstand the fire. There are a number of other things. It was a hostel where people had put in what should have been safe refuge areas. They put furniture and so forth. And that meant that the fire grew very quickly, the walls collapsed, and it resulted in 22 people dying. I would say that the practice of fire safety engineering is to use the best available data, and that's the bit that I'm talking about, as input to predictive models covering the range of probable fire scenarios. Okay, so what I want to talk about now really is the data that you get, because my experience of people who use computer models is that they're very good at using computer models, but they're not very good at actually making sure that the data they use as input to those models is the same as the data as it was measured, if you know that. So, in terms of is the input data fit for purpose, I would define bench scale tests, the sort of things that you were talking about, not large scale configurations, but you've typically got, and the fire propagation apparatus is better than most bench scale tests in the sense that most bench scale tests look at a well-defined, well-ventilated fire scenario, and they're very suitable for looking at the time to ignition, perhaps the early flame spread and the heat release, but they're almost always well-ventilated, and they're very good for addressing the fire or no fire question. Are you going to get ignition? Are you not going to get ignition? But when you look at large fires, they're almost always, they've gone through that transition from well-ventilated to underventilated. They will burn much more slowly because they're underventilated, but in doing so they will produce a very high radiant flux. They'll get a lot of soot particles, they'll act as radiant centres, and that will give out a lot more radiation. And what we find is that it's very difficult to replicate that on a bench scale, to get high enough radiant flux in order to force underventilated burning. And this is what Anna's been doing to look at underventilated burning in terms of the carbon monoxide production, the hydrogen cyanide production, as input to models of fire toxicity. And the question that I'm asking this afternoon is whether you can also use that to improve the models that you have for fires when you're talking about your fire safety engineering assessments. Are you able to properly model underventilated flaming, or are you assuming the worst case scenario of well-ventilated flaming, which is why in the wonderful work Guillermo published, the ability to predict the time to flashover shows a significant variation, should we say, in certainly when you're using FDS. So, in order to achieve stable flaming in oxygen-depleted atmospheres, we need to quantify the ventilation condition, very difficult in a large-scale fire, and this is what we're trying to do in the setup we've got with this half-scale ISO room at Washington Hall. But to get stable flaming in underventilated conditions, We can certainly do it if we can allow, normally in a fire test, in the fire propagation apparatus or the cone calorimeter, you've got a fixed radiant heat flux and a variable rate of burning. If you have a fixed rate of burning and a variable radiant heat flux, then you can achieve steady state burning, which means that you can then have more scope to vary the fire conditions. If you monitor the rate of burning or you control the rate of burning, then you can control, and you control the airflow going to that, then you can force under-ventilated burning, because it's not particularly stable. In a well-ventilated type of test, it tends to go out. So this is the steady state tube furnace. Again, you've seen it once, but I'm sure you'll benefit from seeing it a second time. Essentially, we have a furnace here which, by accident of design, has the highest radiant flux in the middle and zero radiant flux on the outside. So as the sample moves into the furnace, it's exposed to a greater and greater radiant flux until it gets to around the middle, at which point it should have ignited. So we set the temperature in the middle of the furnace, perhaps at 650, and if the ignition temperature is 450, we would expect flaming to stabilise somewhere around here. Just to show you, we then can vary the primary airflow rate between 2 and 10 litres per minute, and then we top it up with secondary air, so we've always got 50 litres a minute coming out as exhaust gas. We take samples of that air for analysis, but we also take some of that air, some of the effluent mixed with lots of fresh air, through a furnace at 900 degrees, and then we measure the CO2 again. So we're measuring the CO2 in here, and we're measuring the CO2 coming out of here, and then we can see how much product of complete combustion we've got in total. If I press the button correctly, you can see my attempt at animating the behaviour in the steady state tube furnace, and we've got the ignition temperature correlates to the temperature in the furnace at which stable flaming occurs. Okay? So this process of the sample going in takes about 20 minutes. So what we've got then is an initial burst of flaming, then more or less steady state behaviour, and then probably an initial sort of burst of flaming as there's no more sample to heat up, and you just get that end effect where you might get a lot more CO2 or a bit more carbon monoxide. So with the benefit of the equivalence ratio, the actual fuel to air ratio, compared to the stoichiometric, or if you like, the chemical fuel to air ratio, if you say one molecule of methane reacts with 1.5 molecules of oxygen to give you 1 molecule of CO2 and 1 molecule of water, then that would be what I meant by the stoichiometric fuel to air ratio. If we then put the actual fuel to air ratio above that, then if we've got an equivalence ratio of 1, we've got exactly the right amount of air. If we've got an equivalence ratio of 1/2, we've got twice as much air as we need. And if we've got an equivalence ratio of 2, we've got twice as much fuel as we've got air to burn it. Okay? You need to know that for the rest of the lecture, otherwise you might as well go to sleep. So, looking at the important message here is these lines down here showing a curve at low equivalence ratio. You've got twice as much air as you need. You've got very low yields of carbon monoxide and of other products of incomplete combustion. As you move up to an equivalence ratio of 1, you're starting to get quite high yields of carbon monoxide, which increases significantly to at least 10 times the amount when well ventilated as it becomes under-ventilated, and that's when the equivalence ratio is only 1.5. Okay? If I take a couple of exceptions, which I'm going to talk about later, indulging me a bit because this is the interest. These are how most cellulosic and other fuels that you need behave. This one is polystyrene, which behaves in a rather odd way, and this one is PVC, which also behaves in an odd way. I'll talk about those as the exceptions, because as a chemist, those are the bits that you get interested in, but the main message is that as you go from well ventilated to under ventilated, the amount of products of incomplete combustion goes up by at least a factor of 10, sometimes 20 or even 50. If we take the partially burnt carbon, there's a bit of an artifact in the results here. I shouldn't really have included them, but if you look at this is taking the CO2 from the secondary oxidizer and comparing it from the CO2 in the mixing chamber, and this is actually data that goes back to the times the last time I did experiments in the lab, and it shows the carbon monoxide yield, the under carbon, the amount of products that are oxidized in the secondary oxidizer, the bits of alkanes, alkenes, soot, goes up from 5 is 0.7 upwards as a product of incomplete combustion in just the same way as the carbon monoxide goes up, with a yield in grams per gram from 0 practically, or even in some cases we had more CO2 in the mixing chamber than we did, perhaps as a result of instrumental error, in the secondary oxidizer. But you can see in all cases we get much higher yields, maybe a third of the carbon comes out unburned, as you might expect, when the equivalence ratio is 1.5. You didn't have enough oxygen there. If we look at the heat of combustion, again, you can see the heat of combustion, as you might expect. You've got less oxygen there, and therefore, taking into account the carbon monoxide, the oxygen concentration. From the oxygen concentration, we can use 13.1 kilojoules released per gram of oxygen consumed, and then thanks to Dougal Drysdale's approximation that if you have carbon and carbon monoxide both present at the same time, then the two will probably cancel each other out. We can see that the heats of combustion are coming out from a well-ventilated level. They're pretty close to the heats of combustion in wonderful books like Halogenated. And if we take the under-ventilated heats of combustion, you can see that they are proportional to the amount of oxygen that's no longer there. So you've got less oxygen available and less oxygen consumed. Now I'm going on to look at the exceptions. Plasticized PVC, if we take ordinary PVC, you can see that despite the different equivalence ratios, we're getting consistently high yields of carbon monoxide. If we take LDPE, you can see the shape of that curve that I was showing you before, shows that dramatic rise in carbon monoxide, which then levels off as you get into very unventilated flaming. So then we tried a piece of PVC cable. One of the nice things about the steady-state tube furnace is it's absolutely brilliant for burning cabling, because it's linear, it burns along the length, and you can get the shielding effect of the outer parts of the cable and the effect of the inner part of the cable burning. And what we saw with this PVC cable is typically a third PVC, a third plasticizer, which you might say is chemically pretty similar to LDPE, just sort of polymerized petrol, but a shorter chain polymerized petrol, and a third chalk. But if you look at the PVC cable, the equivalence ratio, you actually get the highest yield of carbon monoxide, because what you've got is the inhibiting effect of the hydrogen chloride working against the larger amount of hydrocarbon fuel that's there. So we're getting this higher yield, and something coming down a little bit here, a slightly lower carbon monoxide yield than we're getting just with the pure PVC. So we wanted to have a look at a number of aspects of that. In terms of the chemistry, flaming combustion is free radical chemistry to a chemist, and we have particularly the carbon monoxide. The main heat release reaction is carbon monoxide plus the hydroxyl radical to give you CO2, and the hydrogen radical has to beetle back to the earlier stages in the flame in order to regenerate the hydroxyl radical, which can oxidize the CO to CO2. And when you destabilize the flame or you do certain things to it, then you get higher yields of carbon monoxide because you're not getting a complete flame. essentially, when you have halogen radicals there, you take away the hydrogen and hydroxyl radicals, you lose those extra radicals, and therefore you lose the fast reactions. The fast reactions don't occur within the flame, so you get carbon monoxide or products of incomplete combustion leaving the flame. So, in order to establish the effect of CO yield, first of all, whether it's a condensed or gas phase thing, what happened when we had our plasticized PVC cable, we were getting higher yields of carbon monoxide. Is that because of some reactions occurring in the decomposing cable, or is that a gas phase process? So we took pellets, sort of 2 to 4 millimeter diameter pellets of PVC and 2 to 4 millimeter diameter pellets of polyethylene, and just mixed them together and put them into the tube furnace so that we had the same mass of each of the PVC and the LDPE. To look at the effects of temperature and the ventilation condition on the CO yield, also to have a look at the combustion efficiency. And then finally we tried to do the same thing using a material containing brominated flame retardants. So if we take the PVC on its own, that's the same data for the high yield of carbon monoxide for PVC, and then the same data for the LDPE. And then if we take our LDPE PVC mixture at 650, you can see we're getting similar behaviour to we got with the cable. So you can say that must be a gas phase process. We're getting the PVC decomposing here, we're getting the LDPE decomposing here, and in the gas phase we're interfering with the flame reactions to produce more carbon monoxide. If we crank up the temperature to 850, we get very much similar behaviour. And if we crank up the temperature again to 950, sorry, 800 and 950, you can see now we're getting almost LDPE type of lower yields, despite the presence of all these hydrogen chloride molecules and the chlorine radicals. We're losing that beneficial effect. So when the temperature gets up to something like 950, maybe in a developed fire, you actually lose any of this inhibition that you get from the presence of the halogens. You also lose, you have lower CO yields, certainly when you've got well-ventilated flames. Okay, we try that again. Summary of what I've just said. At lower temperatures, well-ventilated conditions, with the conversion of CO to CO2 is inhibited, and the HCl is effective in inhibiting the conversion of CO to CO2 from PVC and LDPE until you get to 950, and then you might say the fire retardant effect that you get from having the halogens there is also lost at the higher temperatures, so the heat release will go up. And there's this anecdotal thing that firefighters say when PVC burns, it really burns. I haven't been able to quantify that statement, but at least I can add a little bit of colour. Okay. If we take the same thing, this is a sample of nylon 6,6 that contains brominated polystyrene, about 20%, some antimony oxide, which is carcinogenous, and glass fibre reinforcement. And we see that we get fairly high yields of carbon monoxide consistently, whether we've got well-ventilated flaming or under-ventilated flaming. And as we go up to 825, we get slight changes in the behaviour, and as we go up to 950, again we get this falling off. So what happens in low temperature flaming at 650, we're getting this high yields of carbon monoxide because we're having inhibition, effective inhibition. But when we get to higher temperatures, then we're losing that inhibition effect, we're losing the flame retardant effect of the brominated polystyrene. And then finally, to look at polystyrene, we get that peculiar effect where polystyrene gives you a high yield of CO in well-ventilated conditions, but a low yield of CO in under-ventilated conditions. So Again, doing the same thing, and this data wasn't specifically collected for this purpose, but at 650 we get a high yield of carbon monoxide across the board, and as we go up to 750 and 850, we start to get a low yield of carbon monoxide at higher temperatures. So we're starting to then get better burning until we go up to the higher temperatures. Okay, and then we can actually do the same thing in terms of hydrocarbon yield, that we're getting lower yields of hydrocarbons at low temperatures, and then as the equivalence ratio goes up, independent of the temperature, we're getting a higher hydrocarbon product, so we complete combustion. Combustion efficiency obviously falls away as we reduce the amount of oxygen that's available. So all the way through, I'm sort of talking about combustion efficiency, the heat release, the contribution to the fire. And so my point is really coming back to the same, well, in terms of input to fire safety engineering models, I'm not sure quite how Fire Dynamic Simulator takes into account under-ventilated flaming, but I certainly have questions about the way it does it. So, good models require good data. Well-ventilated flaming tells us about fire initiation, but doesn't tell us about fires when they actually come to the point of being threatening, and the reason that we're here to try and stop under-ventilating developed fires that are occurring. Ventilation controls fires. Ventilation controlled fires release less heat, more carbon monoxide, more hydrocarbons, tend to burn more slowly. And what I should have finished off with is a slide to say, okay, I started off with the exceptions of PVC and polystyrene. If you crank up the temperature a bit, actually they fall into line and they show the same effect with under-ventilation and well-ventilated flaming as most other materials. Okay, thank you, and I'm afraid I'm still going to plug the book. So.